As a way to introduce acids and bases and the pH scale, I'm going to use the pHet simulator from the University of Colorado. And if you'd like to access this yourself, if you Google pHet, PHET simulation Colorado, and then acid base or pH, you should find it. So we are all probably familiar with the idea of the pH scale, where we have acidic, basic, and neutral. And we're used to thinking about water as being the primary neutral solvent that we would mostly be familiar with. So the pH of neutral water is 7. Anything below 7 on the pH scale, so from 0 to 7, would be considered acidic. And anything above 7 on the pH scale would be considered basic. And we can look at different compounds and look at how acidic or basic they are. Here we have neutral water. I'm going to add a little bit of water so that we can see exactly what our volume is. So we're at 0.7 liters or 700 milliliters. And I'm going to add our little pH probe, and we can see that our pH is 7, neutral water. So let's try a couple of other types of solutions. So let's look at coffee. So coffee gives us a pH of 5. So that is 2 full pH units below neutral water. So coffee would be an acidic solution. Now let's look at drain cleaner. Drain cleaner has a pH of 13. It is very basic. And so this would be drain cleaner like if you have a clog in your pipe and you add a thick drain cleaner to the pipe and you let it sit in there to try and dissolve a clog. That type of drain cleaner, that is mostly sodium hydroxide, which is a fairly strong base. And so that gives us a basic pH. So you can play around with this a little bit if you'd like, but I'm going to switch us to the micro view now. So one thing we can do is look at the concentration of the species that are in solution. So when I say species, I mean the chemical compound. I'm going to go ahead and fill this up to 1 liter. Oops. Let's drain that and fill it to 1 liter. So this will make our calculations very simple. So we can see these concentrations here, and we will look at this in more detail in class, but a couple of things I'd like to point out. This right here where it says H3O+, this is called the hydronium ion. We use this instead of H+, because this is really what's in solution. So you could imagine writing a chemical equation of H2O dissociating or breaking apart into ions. So H2O going to 1 H+ and 1 OH-, which is the hydroxide anion. However, what really happens is that H+ sticks to another water molecule. So we would write this equation as 2 H2O goes to 1 H3O+ and 1 OH-. So 1 hydronium and 1 hydroxide. If you would like to express these as H+, you may do so. But it's important just to not be worried by this. You can think H+ if you need to. You can think H3O+. They are equivalent. Okay, so we have our water solution and we have a pH of 7. And you can see that our concentration of this is really, really small. So pure water, even though it can separate into ions, or it can what we call auto ionize. It doesn't do it to a very large extent because water is pretty stable as a single molecule. Okay, so let's look at this. So if we have our red is our acid, or H3O+, and our blue is our base, hydroxide, OH-, we can see them in here, and we see that we don't have that many of each, but we have equal amounts. So now what happens if we make this more acidic? Well, let's look at coffee. Coffee, with its pH of 5, now we see that our hydronium, or our acid, is more concentrated, and our hydroxide, or base, is much less concentrated. So even though these two numbers, if you multiply them together, you would get the same answer if you multiply these two together as if you multiply water. If you multiply these two together, the product is the same, but you can see that the ratio of one to the other is not the same. So coffee, being more acidic, has a lot of this present. And then if you have a base like drain cleaner, that has a lot of hydroxide. It is 1 times 10 to the minus 1, so it is 0.1 moles per liter of hydroxide, and this is 1 times 10 to the minus 13th moles per liter, which is the same thing as 0.0, and there would be 12 zeros and then the 1 at the very end. So this is an extremely small number. And again, this will become important to use scientific notation. So if you're still struggling with scientific notation, you'll want to take a look at that. So in summary, we have our pH scale. We can look at the hydronium ion, or H+, concentration, and we can look at the hydroxide, or OH- concentration. And it is the concentration of this here that determines what our pH is. So in class, we will practice with some of this, but if you are all set with this vocabulary, you'll be in a great place and ready to do some practice problems with acids, bases, and pH.